Hey everyone, so my name is Brandon Sherman. I'm going to be giving a talk about putting the bits back together. So a little bit about me. I'm a senior cloud security engineer at Twilio. I'm also, in my spare time, a Krav Maga instructor. Getting virtually punched in the face every day in my day job isn't the same thing as that sort of physical interaction. Generally speaking, cloudy outlook on life. Rehearsal, that joke also didn't go well, so hopefully I'll liven up a bit. I am a certified solutions architect, professional grade with Amazon, which really just means that I've been drinking the Amazon Kool-Aid for long enough that I sort of can pretend to know what I'm talking about. It also increases your LinkedIn spam by 20%, so highly recommended. For those of you in the back, that's a big picture of what I look like, wearing much less loud clothes than I am right now. So, what we're going to talk about today. First thing is why. Why is cloud forensics important? Why is it something we want to be investing research time into? We're going to talk about a little bit of background on Amazon Web Services, AWS, and then a few different parts of the services that make up that umbrella, EC2 and EBS. Going to go through the research, methodology, and findings, the really cool part of the talk, and then also a little bit about how you should be protecting your forensic data. So start with why. This is a Twilio value. It's one of my favorite ones. It really forces you to go back and think about what you're trying to accomplish. So why? Well, things happen. Everyone in their job, I'm sure, has experienced at some point something bad has happened. And compromises happen. Like it's a sort of a fact of life, really, that, oh, come on, work with me, technology. All right, so yeah, I meant to fill in the most recent data breach that happened recently, but I forgot to check this morning, or if anyone saw the NPM thing go on, props to you. I'm sure your phone will buzz with a push notification at some point with the most recent vulnerability. So prevention is ideal, but detection is an absolute must. We want to stop bad things from happening, but if we can't, then we have to know what happened, how bad that thing was. So that way we can go back and really know with certainty how bad it was. Is this just a script kiddie, or is this full-on nation-state attacker trying to get into our systems? So that's what a forensic investigation helps us to answer. We are going to investigate some event that happened previously, and we're going to do it using scientific techniques, something that's testable, repeatable, that we can use to show our work. The time to be developing those techniques is not after the event, after the breach. We want to have these things ready to go ahead of time, so that way we have a game plan to follow and aren't just making it up on the fly. Also, for me personally, what's hidden is a lot more interesting than what's visible. So if this attacker has done something like deleted log files or forced those log files to roll over, they've dropped some malware that's then erased itself so it's entirely memory resident. These things that they're trying to hide and why they're trying to hide them, I find to be really the interesting part. Okay, so for the purposes of this talk, when I say the cloud, I mean Amazon Web Services. This isn't supposed to be a knock on Google Cloud or Azure or any of the other cloud providers out there. This is just the one I'm most familiar with. They're sort of the understood leader in the space. A lot of companies are using them or doing work in AWS already. So again, super high level. This isn't going to be an introductory course in AWS. It's also not going to be an advanced course. I'm going to try and just give you what you need to know so that we can understand why my techniques are useful and applicable. And this is also in part because Amazon is comprised of a lot of services. This is a screenshot of the console. When you click the products drop-down and you see all the list of things that Amazon has to offer, this screenshot is also probably outdated by now. There's probably more, or I didn't scroll far enough in my browser. There's a lot there. So I'm going to focus primarily on 4 things. Elastic Cloud Compute, which is the EC2 service. Elastic Block Storage, which is the sort of block storage service. Really creative names. Getting into more of the details of what they are. Identity and Access Management, which is essentially permissions. And S3, the Simple Storage Service. And in case you missed it, this is where those are on that big drop-down list, the eye chart. All right, so EC2 stands for Elastic Cloud Compute. This is virtual machines on demand. You can even get some bare metal instances through Amazon now, which is really interesting. But the bread and butter and the most common use case is virtual machines. They all have varying capabilities, capacities. Some have more disks, some have more RAM, some have more CPU, some are networking optimized. They all have these different levels of capability. They've gone through multiple generations. Click button, get server. It's really simple. If you haven't logged into an AWS account, they're free to create. You get some free trial credits to run small servers for a year. It's really easy to just hit that button and get a server. If you create a script, you can hit an API. You can get lots of servers out of that script. That'll bump you out of the free tier pretty quickly. But this is all controlled through APIs. It's software-defined networking that you're going to also control through software. The default for these instances is something called shared tenancy. Basically, you don't know who your neighbor is. You're running on a fleet of servers, and everyone sits next to everyone. If you need, for your business purposes, you can get dedicated tenancy, various levels of that, to sort of either pick your neighbors and know who you're running next to. So the starting point for any EC2 instance is going to be an AMI, an Amazon Machine Image. This is the data blob that contains the host OS, any configuration. It's basically just the original root disk image. It's possible to create an AMI from a running instance, which is going to include whatever the state of that instance is at the time you create an AMI. So if you have something that's already running Apache and MySQL and you create an AMI out of it, when you launch that AMI, it's going to come up and it's going to also have Apache and MySQL in it. So no sort of cleanup work done in between. Some instances have instant storage and some don't. Shocker. However, there is a really critical difference between instant storage and the block storage we're going to talk about next. With instant storage, everything is ephemeral. It's really, really fast. It's also very fleeting. If something is on this ephemeral disk, then when your instance is stopped or terminated, that data is immediately lost. So if you have malicious content that you're trying to put somewhere and you put it on this ephemeral directly attached storage, and then you as an incident responder come in and say, oh, we need to get rid of the server, we need to terminate it, it's currently engaged in denial of service attack, whatever it is, you've already, like, that ephemeral storage is going to be lost to you. Even more concerning is that there's no way to access this ephemeral storage from outside the instance. So if you don't have a way into that host, if the attacker has denied you access for somehow, then that data is as good as gone. Another way to store data is through EBS, the Elastic Block Storage Service. Here is very similar to EC2. You request a server, you request a volume. You say how big you want it to be, where you want it attached, what mount point, and Amazon handles it for you. It is network attached storage, but it's going to show up locally to your instance. It doesn't know that it's network attached. And there's different backing mechanisms to EBS. So this is a chart showing the 5 different types of EBS volumes there are. Standard was version 1. They got more specialized in version 2, which is the GP2, IO1, ST1, and SC1 types. All different backing materials. Some are hard drive, some are solid state disk. different sizes, throughputs, kind of different prices. Pick what you best suits your needs. But the annualized failure rate for these disks is the really interesting part. It doesn't matter anything else about them. Whatever one you pick, Amazon guarantees that the failure rate is between 0.1 and 0.2%. So EBS has an annual failure rate of less than 0.2%. I guess if they're going to fail less than 0.1%, they induce some failures to guarantee that. I don't know why. But yeah, it's less than 0.2%. If you go out and you buy a hard drive, or you call up your rep and you say, I need 1,000, 10,000 hard drives, those drives are going to have an annualized failure rate of about 4%, give or take the batch, whether they're made on a Friday or a Monday, things like that. And if you go ask the NSA guys in the hall for your data backup, they're going to tell you they don't have it. But they will give you Rhesus, so pretty cool. All right, so the magic part of this. EBS is 20 times more durable than a regular hard drive. Shows up the same. It's made up of the same stuff underneath, deep underneath the hood, but it's 20x more durable. And it's basically, Amazon just says, this is magic. This is some evil voodoo we do and hide you from, and you can have your data stored for better for longer. Okay, so recap of block storage. It's elastic block storage. It is disk storage that is network attached, but has different capabilities. It'll show up on either the NVMe or SATA bus, depending on which type of instance you connect it to. It's dynamically sized, statically allocated, with an asterisk there, because now there are some that you can dynamically resize, but for just this purpose, we're going to talk about the statically allocated ones. And they fail 1/20th as often as a single regular drive, and you can trigger a snapshot of an EBS volume through an API call. You don't need access to the host. You don't have to do anything. Using just Amazon tools, you can get snapshots. Quick note on IAM, this is the permission controls. This says who can do which actions on what resources, when you want them. We'll get into this a little bit more. This is how we're going to protect the chain of custody for an instance, for a volume. But this is sort of what lets us say, oh, I do have permission to take a snapshot. I do have permission to create or terminate an instance. S3. So these EBS volumes that we create, snapshots taken, where does that snapshot end up? It ends up in the cloud bit bucket. It's a S3. It's a key value storage. The snapshots are blobs that get put into a special location in S3. When you take these snapshots, the other cool feature of them is that the disk doesn't have to be detached. There could be a live volume attached to a running, working instance. You trigger that snapshot, and Amazon will give it to you. There could be some data inconsistencies, but generally you will get a very usable snapshot back. The other thing about snapshots is that they're immutable. When they're stored up in S3, it's sort of a versioning marker. If you create more snapshots, you just get more snapshot IDs all stored in the same bucket. They don't overwrite each other. And AMIs are special versions of these snapshots. They've been blessed to be a boot volume. You can use an AMI. The root volume for an instance, what it starts up from, can be either EBS or this ephemeral storage. You can pour an AMI into either one of those and get a running instance. All right, so stop me if you've heard this one before. You've got Alice, you've got Bob, and you have the third party. Alice and Bob are going to communicate with each other through the totally fake, made-up What's My Gram Book service. What's My Gram Book uses one server, and that server had a breach. Alice and Bob want to know, or rather, the owners of What's My Gram Book want to know, were Alice and Bob's communications accessed? What did the attacker do when they got onto that host? So as an investigator trying to figure out what's possible in AWS, we've got a few questions. One, if a snapshot of an EBS volume is taken, will that snapshot only contain in-use blocks, or are the deleted blocks also going to be included? Amazon knows what blocks have been written to. They could just skip the ones that have been deleted. Does it matter, question two, does it matter if that original EBS volume is of different types? Has Amazon changed their implementation between different versions? And 3, does the instance type matter? Does it matter whether it's the newer generation that uses NVMe or the older instances that see this on the SATA bus? So here's the process. Launch a bunch of EC2 instances, attach an EBS volume of the different types to each class of instance, write files, delete files, trigger a snapshot of that disk, rehydrate that snapshot to a new clean EBS volume, and then go fishing. Well, not fishing PH, fishing with F. So here's a screenshot. I wrote the script. Basically, it just says what instance types and what volume types I want it to do, and it multiplies the two together. Get ready to burn some cache. They all come up in the account. I did have to file a support ticket to Amazon and say to increase my account limit so that way I could have this many instances running. It's to protect you from yourself, because if that script had an infinite loop in it, you don't end up owing Amazon infinite money. The other thing I did is I used something called Amazon Systems Manager to run the commands across my fleet of instances. And this command, I'm not going to go into the service too much, but this just meant that I didn't have to go and SSH into every single one of these instances and run a series of commands. I could just say, here's my script, here are the targets, go out, run the command, and tell me if it worked. And here, all it's doing is it's grabbing files out of my C bucket, writing them to the disk, waiting, syncing, trying to flush the disk buffers in case the operating system's doing anything to cache, wait, sync, then it goes ahead and it deletes the files. And then here, right, command successful. The very next thing I'm going to do is I'm going to shut down those instances because I'm not made of money and I don't want to spend any more than I have to. So the What's My Gram book sysadmin / founder / DevOps / their person logs into the Amazon console. They've gotten this notification that they've been breached. They trigger a snapshot of the EBS volumes that were attached to their EC2 instance running the service. Now they need to find out what happened on that volume. Enter PhotoRec. PhotoRec is freely available open source software that looks for deleted files. Really, really cool, great software. Highly recommend it if you've ever lost photos from a camera or something like that on a memory card. And it looks at the raw blocks of a disk, and it tries to compare the data that it sees and it gets back to known file signatures. So we're going to take a forensic script now that I wrote. It's going to take each snapshot that I've taken and put it into AWS. Going to rehydrate that onto a new EBS volume. It's going to attach that new volume to an instance, and then it's going to run PhotoRec and look to see if there's any deleted files that it can spot. So just a screenshot of that script that's going to go ahead and start running. And it just, you can see, this is all running through Systems Manager, so I don't have to SSH into the box. I can just give it the commands. It's going to pull down out of my seed bucket the PhotoRec. So, cool part, results. We actually get a ton of files back. So if anyone here in the audience is from What's My Gram book, be very, very thankful. And also beware of the future. There's a few caveats, though. So if you're trying to do this forensics and you're looking at the root EBS volume, the one that was born from that AMI, which was itself a snapshot, you're going to see tons and tons of files being recovered. That's because it's this overwhelming amount of files are coming back because that AMI was itself a snapshot, and that snapshot had deleted files as a part of that server setup. If you look at AMIs that have been around for or been updated a number of times, and you can trace their lineage back, you can find huge amounts of deleted files coming in from those on those new volumes that they've been poured onto. And that's exactly what I was saying. So they're snapshots, they contain deleted files, and if you use that as the startup volume, you're going to find a lot of recovered files. And so some of you at this point are probably like, okay, show me the proof, which is fair, because I've told you how the story ends without actually telling you how I got there. How do we know it's possible to recover all these files? And, well, I went looking. So we're going to match up some hashes. When you're running any kind of like deleted file recovery, it's sometimes you don't get all the metadata. You don't get file names. You don't always get file types, just a best guess. You get a whole bunch of files back. So, and in this case too, you get a bunch of files that Photorec found that weren't necessarily matched cleanly. This is because Photorec has to do some guessing. It can't handle lots of fragmentation. So especially with files that don't have clear beginning or ends, like text files or source code or log files that are just sort of some bits on disk, no end of file, just go until you don't see any more data. Photorec will do its best, but it may end up getting a bunch of small pieces of that file back. So this is an example, just a few different files, but what's a little bit more cleaner, because you can see they're kind of getting cut off in the middle, is this file, which was just a seed file, text file of a whole bunch of flights, where start time, end time from airport to airport. And it was originally one big text file. But Photorec, when it was doing the recovery, didn't know that. Instead, it just found, actually, that's two pictures there, but it found a lot of this file spread across multiple different recovered images, or recovered files. So a cleaner way than trying to compare the hash of the entire file to the hash of the entire C file to see if I got the entire file back was to check the first about 1,000 bytes. So instead of looking at all of the files, the whole size, because there can be some corruption somewhere in that black magic that is EBS, how you get your files back, you need a more reliable way to figure out if you got at least most of that file. So here's the output of my script, and you can see there's all the different instance types, the different volume types, how many files it got back, and how many of them match. And I'm not expecting anyone to read all this, although if you are, that's pretty cool. But it's, you can see there's frequently more files recovered than were original files there to match. So there are 56 seed files in total. Sometimes got 80, sometimes got 90 back, sometimes got a lot less. The source instance type didn't have any detectable effect on the ability to recover files. Didn't matter how that disk was attached, how old that instance was. Data was able to be recovered. But what did matter was that EVS volume type. So I got really good rates of recovery from the standard, the Gen 1 EBS, as well as GP2 and IO1 file types. Those are the ones that were either the original V1 or solid state backed. Less good recovery rates were the SC1 and ST1 type of EBS volumes. So, and this is a screenshot. I ran through this multiple times. Data stayed pretty consistent. We're able to see here for the GP2, IO1, and standard types, the recovery rate was above almost 90%, 86%, 93%, 89% of the recovered files came back, and the first 1,000 bytes matched. But for these other, the SC1 and ST1 types, a lot less data came back in all. Less than 50%, and cases lower than 20% were also not uncommon. So that's not all. There were some other weird artifacts that only presented with this type of volume. The PDFs in particular, and one particular PDF, just seemed to throw the recovery for a loop. No other drive type had that problem. So this was just my recovery volume. And you can see I got 272 gigs of recovered data back. When I look at the sort of the top files, if you can't speak or convert bits to gigabytes, there you go. 161 gigs for this PDF file. 24, 21 gigs for just this one single page PDF. I don't know why. It's some artifact of the process of storing the data and recovering it resulted in these massive file sizes. And then you can see there are other two MP4 files that came back okay, that were their expected type, and those are other volumes. But this PDF, I don't know why. It could be an issue with the way that these were, the underlying infrastructure is implemented, that just cause the end of file marker for that PDF to be really far away from the source, the start of file marker, but it only appeared for these two types of volumes. This is what the PDF looked like. This is a one-page test image. I don't remember where I got it. It's just some patterns for you to test out your printer with. Don't know. All right. So we know that we can pull data back off of an EBS snapshot. We know that we can take that snapshot, sling it around, put it back onto a new volume and test it out. We can do this multiple times because snapshots are immutable. We can run our recovery multiple times. But we also have to make sure that this data stays protected. No longer can you say, all right, go out into the field, grab that hard drive, put it in that box, put this lock on the box, and then take that whole locked box and put it in another box and lock it up there, and then FedEx it or ship it off or just stand next to it. Don't let anyone touch it. This is all in the cloud. It's all virtual. There is no disk that you can go and just protect or send an intern to watch and tell you if it moves. So the way that you protect data in AWS is by moving it into another account. The limits of an attacker of their account permissions are limited to one account. Your API keys only work in one place. So snapshots can be copied over to another account. This way, if the attacker is in your account, they may not have just compromised your server. They may have compromised your API keys. They may have compromised your Amazon account. They may be able to watch as you take that snapshot, wait for it to complete, and as soon as it completes, delete it. And then you're stuck with no data again. So the way that we want to do this is we want to copy these snapshots as soon as possible into another account to keep them safe. That way, if the attacker is in the account, they can't do any damage. So this is a little graphical overview of an EC2 server, a What's My Gram book server. It's got an EBS volume attached. So we get a nastygram from someone. We learn that it's been compromised. So we start the snapshot process. Wait till the snapshot completes. Then the attacker, who we didn't realize it just yet, comes in with their API keys. They see that snapshot, and they burn it. And then for good measure, they burn the rest of the account down too. This actually happened. There was a company called CodeSpaces that was breached a number of years ago. This was 2015, I believe. And they tried to do an incident response to it themselves. They thought they regained control of the account. They tried to lock the attacker out, and the attacker responded by locking them out again and then just deleting everything. When they finally got Amazon support back on, got able to get back logged into the account, there was a handful of files in S3 left. Everything was gone. So you don't want this to happen. This is really bad. It ends companies. So in this case, we're going to go through the same scenario, get a nastygram. We know we've got to copy that snapshot to a new place. So we triggered the snapshot. We copy it into a secondary account, an incident response account only used by security to do their work. And then we're going to do the forensics in this account. Which also makes some amount of sense, right? We want to do forensics in a quasi-offline environment. We don't want to be doing forensics in the same place that the attack happened. So now, if our attacker does come in and does try and delete everything, we still have a snapshot that they haven't been able to touch, the proof of their intrusion. If they try and delete that snapshot, they can't. Their credentials don't work on their account, leaving them very, very sad. All right, so what are some takeaways here? This really depends on what your threat model looks like. If you are concerned about having access to the highest quality forensics possible, and cost be damned, infrastructure layout be damned, you need to be able to guarantee that you can get good quality forensics, you probably should stay away from using the SC1 and ST1 type EBS volumes and stay away from using ephemeral storage of any kind. If not, then know the limitations of doing forensics on things that are not that are these volume types. You may end up having very strange artifacts. You may expect, okay, from a 10 gigabyte drive, I'm only going to be able to recover maybe 8, 9 gigs worth of stuff. Instead, you may get back multiple very large PDFs. I don't know. Let me know if you find out or what happens, because that might happen. You just need to be aware that this is a possibility. Consider only doing writes to non-root volumes, especially logging. So your root volume is going to have a ton of artifacts left over from that AMI creation process, from the AMIs that came before it, by its grandfather and its grandfather before that. So if you're worried about losing the signal for the noise, only do your writes to a non-root volume. EBS volumes are going to show up as clean, nothing there, no cross-contamination from other account owners or other AWS accounts, which means that if there's only writes happening to that volume, you're able to pull back things that you know were on that volume and aren't artifacts of previous processes. So the other thing, use multiple accounts. This is a big thing. Everyone who knows me likes to tease me for it, but it's true. Amazon accounts are free to create. You can have as many of them as you want. They also then all qualify for the free tier, which isn't really that big of a help. But with multiple accounts, the breach of one server now in the cloud could mean the breach of all of your stuff, not just servers. We see it very frequently that someone will launch a server and they can't figure out the permissions to get it to work. So they just say, all right, I'm going to give this server the EC2 star permission. You can do anything in the EC2 category of permissions, which could be launching more servers, could be terminating any other server. You see this with build hosts, like Jenkins, where it needs the ability to launch servers to test against, to build against. So that has those credentials already. Compromise there could mean not just that server is toast, but everything else that server has the permission to destroy. The other thing is a loss of an API key could mean the loss of all of your stuff. If you're trying to do incident response and you've got a snapshot, you're working on figuring out what's happened in this Amazon account, the account limit is the blast radius. It will prevent that API key from being useful outside of that account. You have no power here. So keep your forensics outside of that blast radius. So thank you all very much for your time and your attention. A couple of quick things. We're hiring. If you know of someone you're interested, you know someone that you want to subject to working with me, sign up. We have a bug bounty program. So go ahead if you're not like, oh, what's this Twilio thing? That seems kind of cool, and that might be fun to break. Please do so, and then tell us about it. We do payout. And then if you want my business card, go ahead and text 213-27-SHAKA to get my email address. Thank you. Any questions?